right, so let's kick things off. So thanks everyone for coming to Lonestar. By show of hands, I'd like to ask who has used Phoenix in production? Present? Wow, that's awesome. That's what I like to hear. Okay, so today we're talking about Phoenix, obviously, but before we do that, I need to plug Dockyard. So for those of you that don't know, I work for Dockyard. We're a Ember and Elixir consultancy, and Dockyard pays me to spend the majority of my time working on Phoenix itself. So we owe them a huge thank you, and we do consulting. So if you need help on anything Elixir related, check us out. We hired Paul Schoenfelder, Bitwalker Paul, of Distillery for Elixir to work on the problem of solving deployment and releases in Elixir. So Dockyard is investing heavily in the community and our tooling. So check us out if you need help with anything, or just give us a shout on Twitter. But we're talking about Phoenix 1.3 today. Just kidding. Phoenix 1.4. I spent the whole last year talking about 1.3, so I'm tired of it. It's been released. But no, we're talking about 1.4, and it's not going to be this 8-month late project. So things are shaping up pretty well. No big changes, even though 1.3 wasn't like breaking changes. The whole idea of context was a bigger shift, but 1.4 is just going to be kind of nice, shiny features. So we're going to talk about 1.4 for a little bit, and then I want to get into kind of the problems that we want to solve long-term with distributed systems and how to think about solving those problems. But the big feature for Phoenix 1.4 is HTTP 2, and you can just drop Cowboy 2.0 in your mixed dependencies, and you'll get HTTP 2 support. So we're doing some gymnastics internally. We'll detect if you're running Cowboy 1 or 2 and just load the right adapter. But by default, we're still going to ship with Cowboy 1. So Cowboy was released as stable. If you're using it in production, Cowboy 2, please let me know, because there was an issue where someone was getting content out of order in Safari using HTTP 2 with Cowboy. And that was after like 2-point releases. So we're kind of going to let things stabilize a little bit before shipping it to everyone in the wild, but it's there on master in Phoenix if you want to use it, and then Phoenix 1.4 will just be a one-line mixed config change. And then at some point in the near future, we'll ship with it by default, but it's opt-in today. And really the biggest feature that interests me with H2 is H2 push. Otherwise, it's just like HTTP 1, especially because there's no JavaScript API to like open up a connection to HTTP 2 server, which is bizarre. Like I thought like we made this channel layer, and I was trying to give myself a pat on the back because it speaks WebSockets and long polling. And I was going to say, like, look how great it is that we were able to just use a HTTP 2 transport in Phoenix channels, but there's no JavaScript API. So, like, you might hear people say you don't need WebSockets anymore because HTTP 2 does bidirectional communication, but not from the browser. So Gary Rennie on the Phoenix core team, he wrote an HTTP 2 channel transport. So if you have a server, you can speak to a Phoenix channel over H2, but a browser can't do it. But it can do other neat things. So H2 push is a way to send assets down to a browser as it's loading the page. So you're going to be able to get some performance benefits if you're running H2, and you can just plug push and push an asset down. So what happens is the browser is loading a page. We're able to tell it as it's loading that page, hey, by the way, here's your app.js, here's a logo. And then when it's parsing your markup, let's say, it's going to come down and say, oh, actually, you already pushed this logo to me. So I don't have to make a new HTTP connection to go fetch that, which is kind of cool, and it's neat because like we have all these years of developer time going into like JavaScript concatenation, and I still think we need those tools, but it seems like it's funny that we might go long term. We might end up just pushing like 12 scripts down to the browser, just like we used to before we cared about performance. But the crazy idea is that I don't think we'll do, but one thing that Gary and I were talking about on the core team was like, technically we could take static path, and if you're running HTTP 2, we could just push from the template to the client. So the problem with H2 push is like, I have to know every asset I want to push down. So if you go back to the controller, you'll have this coupling between okay, I want to push app.js, obviously, probably always, but what if I'm rendering dynamic content? What if I'm rendering a profile photo and I'm not using a CDN? I have to kind of know the things I need to push before I actually write that code in the browser that renders the asset. So I don't I think it's too crazy to do by default. Maybe it will be opt-in, or maybe it'll be a new function. But technically, we can make our templates impure in static path. Anytime you use static path and you turn HTTP2 on, it could just push down to the browser when you call it render, which is a side effect. So it's like, it violates a lot of things, because like you could just, today a template is just a function, and you render it, you get a string or IO data back. So we'd be like sending a response out of a template render, which is weird. But as an opt-in thing, it could be cool, because you could just write your templates like you're used to, render dynamic content, and just push that all down to the browser automatically. So we're exploring that. By default, it'd be a bad idea, but maybe if it was like an option or some kind of explicit function call, so instead of static path, I don't know what we can name it, but to give some idea that, hey, this is going to be a side effect operation, but then you don't have to manage this coupling between the controller. So we're exploring those ideas, but today you can use H2 push on Phoenix Master with Cowboy 2. And we're innovating in other ways. So we're going with explicit router functions. So today on Phoenix 1.3 and prior, you could say like redirect to job path, and it reads nicely. It's short and sweet. But what we were running into is newcomers or even seasoned developers were we were having our router helpers imported into your controllers by default and your templates, and you would kind of have this function seemingly appear out of nowhere. And since the router helper functions are auto-generated from your router, like you couldn't search the project. So it would almost be like, where is this function defined? And you try to look up in the docs, and you couldn't find it anywhere. So we're doing some innovation. So now in Phoenix 1.4, there's going to be routes job path. So we're introducing an explicit alias just to make this a little clearer at the cost of like slightly more typing. And it turns out there's also some compile time. Your code compilation would be faster using this, but the biggest push is to get rid of this implicit bag of functions that you don't actually write yourself. And especially if you're using multiple routers, you'll be able to just say like API routes or just routes. So what we're doing in Phoenix 1.4 is in your WebEx file today, you just have an alias app web router helpers. We're killing the word helpers. We borrowed that naming scheme from Rails, and because Jose and I both came from Rails, and it turns out like it's weird thinking back now, because like if you're coming from a Rails background, helpers are like almost this mixed-in module, so it's almost like a bag of functions. So you have like application helper, router helpers, but in Elixir, like a module is just a bag of functions. So the word helper isn't helpful at all in functional programming in my mind. So like everything is a helper. So in Phoenix 1.4, we're moving away from that naming scheme, but it's backwards. It'd be backwards incompatible to just suddenly redefine your router as a new namespace. So in Phoenix 1.4, new apps will have a alias as routes, and then once we go 2.0, you'll actually just have a literal module appWebRouter.routes. But in the intermediate time, you'll just have this alias, and we think that's going to lead to clearer code. Yeah, and another thing is we have a faster development compilation cycle now. So I like to say for refresh-driven development, this is an exaggeration, obviously, but one thing we were seeing is like you would touch some file in your app, and you would run the server or run mix compile, and you would compile like every file in the project. And it's bizarre because you're like, I didn't touch any of those files. What's going on? And it turns out the Phoenix router was to blame for this. So it was leading to, I wouldn't say not excruciatingly long compile times, but you're used to like this kind of instant development experience, and it would be like suddenly you have to wait for the whole app to compile just to refresh, text on a web page. So digging down into this, it turned out it was the Phoenix router and ultimately like plug that was causing compile time references. So it wasn't like a issue with the Elixir compiler. So as I want to deep dive a little bit to explain why this was happening, and don't come away with the impression that like it was a compiler issue. It was just we were creating a lot of compile time references. So what would happen is like in your router, you would say, I want to not crackle into this microphone. You would say, I want to plug this user authentication. And at compile time, we take those list of options and we can do some work on those. So at runtime, we don't have to like munge this option list every time. So you would write your plug like this, where you'd say, okay, every plug has to have an init function that takes those options, and then a call function that gets run for every request. And the key thing to understand is those options, session key, like UID, so we could like configure which cookie to look up. That is munged at compile time. So auth user init is called at compile time, and it's going to like default the key to user ID. It's going to convert it to a map, so it's faster to look up at runtime. And then at runtime, that literal map that you munged around is passed in. So we're not expending that cost for every request to kind of munge that data together. So it's a nice feature in Plug to have this compile time optimization, but this ultimately led to our development issues. Because if we expand the code that Plug produces, so we jump into what code is actually produced at compile time, you're going to be using a plug in a pipeline, and then when you run plug, and it's going to produce this AST that actually just is a bunch of nested case statements. So if you have like a plug pipeline, you're going to fetch the session, you're going to fetch the flash messages, then you're going to say, I want to authenticate. It actually turns that into just a bunch of case statements. So it's going to like call case auth user call, and then within that, if the plug isn't halted, it's going to have a nested case. Fetch the flash. If that didn't halt, it's going to have a nested case. So your router plug pipelines literally just becomes a bunch of nested case statements. That would be awful to write by hand, but at compile time, it's super fast. And here's where we can see the compile time references start to build up, because if we check out the literal value that was baked into your program, like you'll actually have a case statement with call, so every request comes in, we pass a connection to it, and then that literal map of session key UID, that would be baked into the program because we generated it at compile time. So this is like a really neat metaprogramming optimization. It's fast because we don't have to, if we were getting like 10,000 requests per second, we don't have to like take a keyword list, default it, convert it to a map for 10,000 times a second. We can just do that once. So this is really cool. We want to keep this. But what was happening is at compile time, since we were calling auth user init, if that plug happened to call into your like accounts context, or it would touch your user struct, you would end up having this cascading list of compiler references, where the Elixir compiler would say like, I need to now recompile your count system, and your count system touched the user app, which reached into another module, and it would just be this cascading list, and that's when people would see this massive recompilation, even though they just touched a file somewhere. So what we can do is in development, like we still want this compilation optimization for production and for test, but in development, the Phoenix team introduced this plug init mode. So we can say we want to tell plug the plug builder has a new option called init mode, and you can configure it on Phoenix where it will produce this nested case statement, but instead of calling the plug init at compile time, we can actually just bake it into the program at runtime. So in development now, your program, when it's compiled, is going to produce code like this, where every request is going to call auth user init and do that defaulting. But in development, you would never experience a slowdown from this. Like this is a micro optimization as far as like your local development is concerned. So we get the compile time benefits in development for like refresh-driven development, and in production, we'll get the runtime benefits of the optimization. So a little deep dive into metaprogramming there, and just to explain why we were seeing long compile times. So in Phoenix 1.4, that goes away. So if you are experiencing this issue today, I would actually like to talk to you to see the kind of benefits we're able to get on Master Branch today. We have some JavaScript changes. So I don't know, I haven't announced this yet. Not a big change, but there is actually a massive race condition in the Presence JavaScript today. So if you're running Phoenix Presence, you have a race condition in your app guaranteed. You may not have experienced it yet, but the only way to solve it was to make a new Presence API, because we have to track the connection lifecycle changes. So this is the old API. So like a bit of bad news, like, hey, your app is broken in some ways today. But the good news is the new API is actually pretty nice, and you need to use it to fix that race condition. But this is the old API. So the old API, you used to have to know that your channel was going to send you these seemingly arbitrary present state and presence diff events, and then you called this pure presence functional API, like presence sync state and presence seek diff. So when we wrote this, we were like, hey, let's just write this pure API. You pass in your present state, you get new state back, because functional programming is fun. And it's a nice API, but it turns out like we have to throw that away now because it can't be pure anymore because we have to track internal state that's going to change on the channel. So the new API is going to be instance-based. So we're no longer using this pure API, but it's still used internally. So if you're running the presence, Phoenix.js includes the Phoenix presence JavaScript. If you're running Phoenix.js and you drop the updated API in place, it's still going to continue to work with the old API. So it's not going to be a breaking change. You'll want to upgrade to this new API. So in Phoenix 1.4, you'll be able to say, give me a new presence instance, and you pass your channel in, and we'll wire up all those arbitrary events for you. So the only thing you really need to care about now is the single on-sync event, instead of those diff and present state, presence diff events, and then you can optionally invoke the on-join and on-leave callbacks in case you want to handle what happens if an individual user comes and goes in the app. So it's a new, nicer API to write, and it resolves race condition. So that'll be out very soon. And really that's it for the Phoenix 1.4 changes. It's going to be out, I said, real soon. It's not going to be like 1.3. There's not going to be a big giant lag time. There's some internal channel architecture that we want to change that's not user-facing. Like your channels today, your channel processes can't be hot code upgraded. So there's some internal changes we want to support there. But at user-facing changes-wise, that shouldn't be anything that you have to really worry about. So keep an eye out for that in the Phoenix book. So Programming Phoenix 1.3 has been like, it was supposed to be released at the end of the year, and then it was pushed back, and now it got pushed back a little bit more. But it's actually, we're just going to leapfrog. The Phoenix book is going to be Phoenix 1.4. So it's not going to be like we release Phoenix 1.4 and then the 1.3 book is released after that. It's going to be future-proofed. So hopefully they'll be released in lockstep, but I don't have firm dates. But the book is going to be coming out, and it will be up to date with everything we've talked about so far. But I want to spend the rest of the talk talking about kind of handling stateless and stateful applications. Because I think this is a really exciting time in the community that like we're starting to not eat the world yet, but we're getting mainstream. We're seeing more and more people adopt the language, and more people use Phoenix. And I think the vast majority of like clients coming into Dockyard are using mostly this stateless approach, where they have like a PHP or a Ruby app, and they're used to the stateless request response lifecycle, load stuff from the database, and then they drop Phoenix in place, and they continue that mindset, and they get like incredible business value out of it. So to me, that's, some people say like, oh, people aren't leveraging OTP, but for me, that's really exciting because like we're delivering compelling business value, and like people haven't even scratched the surface on what we can do. So I want to start talking about like we have this kind of like whole new world of features in the language, and people are rightfully excited about them, but we need to have the right mental model on like how do we actually handle stateful applications now. And stateless applications, especially over HTTP, have their place. So it's like, how do we reconcile these two worlds, and what are the kinds of issues we need to think about? Because, like I said, we have this whole new world where I can develop an umbrella application or a list of different applications, and like if I'm building an e-commerce store, I can have one app handle all of the e-commerce business logic, and then I could have a commerce web app that was just like the web node that called into my e-commerce store. And then if I'm actually holding inventory in warehouses, I could have another app that handled warehouse inventory. Because if you've ever handled any kind of fulfillment or warehousing system, usually they're terrible in my experience. Like if you've ever done this professionally, like warehouses actually have just like CSVs, the little like FTP somewhere, and you have to like pull those down and then like reconcile that with your local stocks. So you'll probably like if you're actually building this in real life, like this is just a trivial example, you'll probably have a separate app doing all that data fetching and management. But the coolest thing is I can develop these three applications locally and just run, mix run, and I'm running those three apps inside one VM. And somewhere, if I want to call into the warehouse in my code, I can just call a warehouse, a process or a registered name, and tell it to decrement some stock for me. And if I deploy this to a series of 6 servers, if I'm getting a lot of traffic, I'll want to load balance on the web front end, right? So I might have 3 commerce web apps running on 3 separate servers, and then those things are just calling in to ultimately, they might do a gen server call into the warehouse. or send a message to some process, and the fact that that's running on different servers doesn't change my code at all in an idealistic scenario, right? So for me, like, this is the holy grail, especially when I was coming into early in Elixir, where I could spin up 2 different nodes and just do like a send in IEX, and then see the message queue in the other node, get that message. Like, that was an amazing feeling, because most of the time, like, this microservice movement that people are adopting is gonna, like, they stand up JSON APIs between their applications. So you have to, like, just to send a message to, like, decrement some stock, it's like, okay, now we need to start an HTTP server on each node, come up with some protocol to parse the JSON, authenticate those requests. It's like all that falls away. We just send them a message to a process. And I've seen this in the wild. So there was a company that built a like massive multiplayer online game, and to high scale, so like millions of users. And it was an Elixir, and they wanted to, they needed to make some game admin interface, so like they could go in and tweak the world settings. And what they did is they just spun up a Phoenix app, and ultimately the Phoenix controller just ultimately ended up doing a gen server call into a process running on the game server, and like that was it. That was enough to accomplish their task. So like to introduce this new feature on their platform, it wasn't like, oh, well, shoot, how do we call into the game server now? Do we need to have that team run a web server on the side and speak JSON, or do we need to throw a message queue in between the apps? Do we need to like put gRPC in there? It was like, no, they just did a gen server call to a server that they already wrote. So for me, like, this is incredibly exciting. So I think I want to walk through, when people start internalizing that these things are possible, they get really excited. And I want to walk through the process of, like, this is what we should be thinking about, but let's not throw the baby out with the bathwater on building traditional stateless applications. Because it feels really good when you come into this mindset. You start thinking like, okay, like if you're coming like me from a mainly web background, I did PHP and Ruby, or if you're, I mean, most people coming from a web background, whether pretty much any language, are used to this stateless mindset of like, we rely on the database, request comes in, we load our state, we throw it away. So now we come into Elixir, we can do stateful applications. We realize that, hey, a lot of these languages and frameworks made us be overly concerned on the database. And then we say like, well, Elixir was built for stateful systems, and we can message a process anywhere on the cluster. Like, if we can do all those things, like, we probably don't need the database for some problems. And like, this is a good mindset. But I think I'm going to crush people's worlds a little bit when like we can get excited about this, but we need to think about the different problems that come when we hit this mindset. So I'm going to do some trivial examples and see how the kinds of things we want to think about. So let's like build a tic-tac-toe game. And let's say that we want to store a leaderboard to show that I am the best at tic-tac-toe. And the leaderboard is going to be persistent, because if we restart the cluster, I still want to be in first place. But this game otherwise is going to have some kind of state that we hold. So as each player makes a move, we need to wait for the next player. We can't allow someone just to keep making their own moves. So there's going to have to be some logic there. And we could put this in the database, but then, why would we put these moves in the database if we have this stateful platform available to us? So if you're in Elixir, you'll probably write something like this, where you're like, okay, tic-tac-toe game, we're going to start a gen server. Our API is going to be super simple because you just mark a player at a position. So it's going to have to do very little. It probably will handle one message. You'll have some game logic that says, like, can that player actually take the turn now? Is it a valid move? But ultimately, you don't care about like persisting those game results. So James Edward Gray and Nathan Long gave a really great talk, I believe last year at Lonestar, about building this game. And like, you're using the primitives of the language, and you don't even think about the database till the very end, or when you need to think about it. And it gives you this really great feeling, because you're like, I didn't have to think about how was I going to integrate database, or how am I going to drop Ecto in the project. You just write a stateful game, and then you're like, oh, well, now I want to persist the results. And then when you're ready to write that part, you're like, okay, let's persist the results. And here's maybe where you would talk to an Ecto repo and just do an insert into your game database. But the cool thing is, all of the intermediate turns are just handled in that stateful process, and we only persist the things we care about. So these kind of ideas, I want people to internalize, because like, they feel good, they leverage the platform, And even from like a performance mindset, like imagine one person on the web browser abandons their game. So you leave the other person hanging on the tic-tac-toe game. We can just say, okay, well, if we don't get a message in 10 minutes, we can just stop the process. So we may never even have to touch the database at all to start this tic-tac-toe game up and then shut it down. We only touch it when we need to. So that feels really good. And what we need to think about is like when you're building these stateful systems, it's like, okay, we have ephemeral state and we have persistent state. And if we're able to figure out like the differences between those two, we can determine when and when we shouldn't reach for the database. Because as you're playing tic-tac-toe, the caller is going to ultimately call like player X, mark this position. It's going to do a gen server call. Like all of these steps are going to be ephemeral, right? Like we don't really care what order they happened in. We're only caring about showing the higher leaderboard. So this is ephemeral state, going back and forth. We're not concerned with persisting this. If the process dies or we restart the cluster, it's like, sorry, your game is lost. You can start a new tic-tac-toe game. So this is ephemeral state going back and forth. I would say, several, not many dozens of steps, but let's say several steps in tic-tac-toe. We don't care about persisting. And then someone wins, and this is when we call the database and we persist the results. So you write an application like this, and like it feels amazing. You're like, I didn't have to touch the database at all. I dropped ecto in at the very end, or maybe I just did a raw insert into some data store, and like this feels really good. And this is the optimal way to write this. So this is great. But the problem is, if you write that game and you have some ephemeral state, it feels really good, but then you come into Phoenix, you run the Phoenix generators, and you're like, oh, I'm writing a CMS, and what is this code that Phoenix generated for me? Oh, it's creating this page content. And then you check out the context, and you're like, what is this? A repo? Like, it's talking to, why is Phoenix touching the database by default? Like, why isn't it starting a process? So I think we need to address these two different worlds, right? Because I think it feels so good to write a stateful application in a language that can properly handle these processes holding their own state, that it feels so good that then you then think the database is bad, or you then think that the web suddenly becomes stateful. So I think people need to handle these two different ideas because they're different. Like if you're writing a CMS, like it turns out that like writing a news website is very different than writing a multiplayer game that happens in real time, right? And these handle state in different ways. So it turns out that the outline.com is running on Phoenix, so real example, and I love this website, by the way, but I'm just saying like they're serving articles up that are going to exist for years, right? It's a news website. Those absolutely should exist in the database somewhere. Like they need to be in cold storage somewhere. They shouldn't be running in a process as like ephemeral state, right? But if you're running on this game on the right, this was, it looks like a video, but it's just a screenshot of a tweet. I'll have to link it, but it's really neat that someone for a hackathon used a Phoenix channel stateful application running this game where like everyone would join from like there's 4 people with their phone in a web browser controlling another screen that you see in the center of like their dot. So in real time, they're sending thousands of messages to control their dot. Like those aren't, you're not storing each of those on touch move events from the phone in the database. Like there's a ton of ephemeral state there that and all those players' positions are being modeled in a process. But we only care about the end results. Maybe we'll show the users that we're in the game and who won. So these are very different problems, and I think we need to understand that sometimes the database is exactly what we want, and other times we need to understand that we're in this new paradigm now where we don't even need to think about the database maybe, or we only need to think about it as kind of this afterthought to persist the state when we want to. So I want to talk a little bit about like, okay, if we're able to understand ephemeral versus persistent state, we need to understand that like the database actually solves a ton of problems for us, because we'll have clients come into Dockyard and they leverage the features of the platform and they think like, oh, I don't need the database. And then you're like, well, are you going to deploy this on more than one server? And they're like, oh yeah, I need to have redundancy. And then you're like, well, how are you going to handle data replication? And then they're like, oh. And then so sometimes they're like, oh yeah, you're right, we do need a database. And then, or they think like, oh, we'll just replicate. And then you're like, okay, how are you gonna handle backups? What about the consistency of that data? So like eventually, you have them think like, wow, you just recreated a really bad database. So these problems have been solved over the last however many decades, so the database exists for a reason. And the moment we step outside of it, it's not a bad thing, but if we step outside of the guarantees that we're used to having, we need to know which questions to ask ourselves. Because if you're like me, coming from mainly web background, you come into distributed systems and you're like, wow, all these questions and problems I didn't know I had suddenly exist. Like it's a whole new world for me. So I was trying to come up with this idea to kind of help people internalize this. And then I was like, oh, you know what? I thought in my head, like, guarantees in a distributed system is kind of like a choose your own adventure game. So I wanted to put that on a slide, and then I started looking up for covers. So like the choose your own adventure, if you ever read the books, like it's like at each step in the book you can say like, I don't know, walk into the forest or continue down the path, and it changes the ending. But it was awesome because I found this cover, and then I looked at the book description, and like it exactly describes a distributed system and the guarantees that you need. So like it's like you are the star of each story. So like now in a distributed system, like you have to start answering yourself what kind of guarantees you want. And then, what happens will depend on the decisions that you make underscored. So like in a distributed system, the guarantees you want, like you have to answer those questions. There's no magic that can be applied there. Like Joe Armstrong, the creator of Erlang, likes to say that you can't like evade or change the laws of physics. So like if you think you can operate a distributed system and like just pretend it's not, like there's no way to go about that. Like we can't just suddenly change the laws of physics. So like we have to start making decisions. And I even like that it was like you'll travel to foreign lands and you'll go back and forth in time. So like if you're into distributed systems at all, like even the idea of like wall clock time, like you can't rely on that. So like you might think like, oh, I can solve this easily because I'll just include a timestamp on this event that happened, and I'll send it to another server, they'll check their time, they can figure out which happened first. It's like, no, surprise, that you can't do that. There's time drift, the speed of light comes into play. So it really is like a choose your own adventure game. And the end result is something that you have to decide for yourself what you want. So this takes, like it used to be like, oh, we'll just shove it in the database. And suddenly the problem is more granular because you have to say, what kind of problem do I have? And how do I want this problem to be solved? And then sometimes you want what the database gives you, or other times you might want to be more lenient, but you have to decide for yourself. And then in looking for these covers, I found like a bunch of parody covers, which was pretty awesome. So I think this describes distributed systems well, in that like, you're the star of the story, choose from 20 tragic endings, and then like, don't bother, you die in most of the endings anyway. Like this is a caution in that like we have these amazing features, but it could quickly spiral into pain and misery. Because like I'm going to pick on MongoDB because I've both used it in production, so I feel like I can rant a little bit. But like you look at MongoDB, which was a database, right? But they handed replicate. Sorry, that wasn't even like I didn't mean to be facetious there. Like I was gonna say like I'm talking about not touching the database, and I mentioned MongoDB, which is a database, and quotes. Anyway, but it's distributed. But you look at MongoDB, and companies adopted it like cryptocurrency companies, and they found out like, oh shoot, like ACID transactions like actually were an important thing, and now people stole like millions of dollars because they didn't think about the guarantees they needed. They were like, oh, distributed systems, replication, money, and so anyway, and it ended tragically. So just keep in mind, like when you have to start. If you have to start thinking about guarantees, and if you're not thinking about those things and you're operating a distributed system, it can end in tragedy. So I want to walk you through that mindset a little more. So I'm going to use a rate limiter example. So let's say our client comes to us and they say, we want a rate limit request to our application. So we could have like a free tier. Let's say we're writing like a geolocation service. People can ping our API and they can pay for a certain amount of requests per minute. If you start thinking about this problem, you're like, okay, do I need the database for this problem? Is how it should start, right? And then you have to ask yourself, like, well, what kind of guarantees do I want? And for a rate limiter system, it's like, well, if we think about like the performance aspect, if we want to rate limit our API, that means every request coming into the API is going to have to touch the database. So if we do that and we're at a high throughput API, like that could really crush our performance, right? If every request comes in and hits a plug that has to go fetch the user, check their rate limit requests, or insert or update a value, that's going to be a pretty big performance hog. Like we probably, if we're on over one node, we might be reaching across the network to talk to the database. So I think we can say like, well, it might be a good idea not to touch the database in this case, right? So when a request comes in, we can have the simple API that does rate limiter log. It returns OK. We call our controller. If it says they're rate limited, we halt, right? That's what we want. We probably don't want to touch the database. So we can write that on one slide. I did a blog post on this, but I didn't include the spoiler alert, which I'll talk about in the next slide. So let's say you write this. You say, OK, we don't need the database. We want to be ROF scale. So we're going to use ETS, which is Erlang term storage, which is an in-memory data store in Erlang, which is incredible. So ETS continues to blow me away, other than the API. So like that case ETS update counter is like, it's incredible what that does. That's an atomic update. So like I don't even have to message a process. I can do this atomic operation without even talking to a process. So I'm able to avoid those single process bottleneck. Multiple callers can call this. It's going to be atomic, but like the API is always like unintelligible. And then like if you get anything wrong, like this tuple syntax, like I just kept trying it in IEX until it stopped throwing argument error. So if you're using ETS, if you do anything wrong, it's an argument error, and that's all it says. Like, you know, you're used to Elixir where it's like, oh, we expect you to pass a tuple here, and you passed, argument error is all you get. So keep that in mind. ETS is amazing, but its API is frustrating. But we can use ETS here, and then our process is going to be, our rate limiter is just going to be a gen server, and all it's going to do is start or create an ETS table, and then every minute it just deletes it. So that way we can get our requests per minute coming in. Each user hits the API, they do a simple in-memory lookup atomic counter update. It's going to be super fast, it's going to allow concurrent access, and then if they are over that request per minute, they get rejected. So this is going to scale super well. So this feels really good, right? ETS, in-memory storage, rate limiter log, the super simple API. We write it on our laptop, and we're in this zen state. We're like, I didn't need the database. Elixir's so amazing. The database is bad. And then you deploy it on your load balanced cluster, and it doesn't work at all. But the problem is, no, it actually works exactly as you wrote it, but now you're load balancing, you're rate limiting each node that your user happens to load balance to, which your load balancer may be randomly shifting those users. So you can't, so you're counting you're rate limiting each node. So if I happen to load balance from node 1 to 2 after I exhausted 90% of my requests, well, congratulations, I get a bunch of free requests. So we weren't thinking about distributed systems at all in that case, because we were like, the database is bad. So what do we do in this case? Like I said, I probably would still want to avoid the database. I think in this case it warrants it. So we need to be able to handle this on the whole cluster, right? It becomes a distributed programming problem. And to show you how complex this can get quickly, let's say like, okay, let's add some replication features to this, right? So if we have state on one node, we need to replicate that state across the cluster. That way everyone knows the counts that each of the nodes have. So you can introduce a little bit more code. You could use PG2, which is built into Erlang. It's a process group, distributed process group. So I could say, okay, every node's going to run a rate limiter like it used to, but except they all join a process group. And then every 10 seconds, I'm going to actually just send myself a message, and I'm going to go through my ETS table and convert it to a list, and I'm going to send everyone all of my data. So I'm doing some advanced replication. Like this is probably what the Mongo code base looks like right here. But no, I shouldn't hate. I think apparently the last release is really good. But we can replicate our limits, and we send everyone our whole state. And the crazy thing with ETS is I was getting ready to add a caveat to this program. I was like, well, but you're sending everyone your whole entire state. So like imagine if you had 50,000 active users per minute, then you'd have to send a whole 50,000 ETS table across the network. And I benchmarked it in IEX, and it was like absurdly fast. Like doing this took like a list of 100,000 entries. So when I get that replicate message, I have to go through all of their user IDs and rate limit counts, and then call update counter myself, 50,000 times in serial. And like this took 0.02 seconds for a list of I think 50 to 100,000 users. So like this would actually be viable if you had 50 to 100,000 users per minute. This would scale like totally fine. But we need to think about the guarantees we have in this system, right? Because as written, I'm only replicating my data. I'm not doing it constantly because I'm not sending an nets table over every time someone bumps my count. I can't just send that data over. So now we have to think about the guarantees we want. And in this case, we're only replicating every 10 seconds. So we're going to always be potentially 10 seconds behind on any given node. And this is where we're like, okay, well, is that an okay guarantee? So if you're writing a rate limiter and you're doing like a geolocation API, we can say like, yeah, that's fine. Like if one user happens to get 100 extra requests to our API that minute because we were 10 seconds behind replicating their other load balance nodes, like that's totally fine. For us, like rate limiting, I think in the general sense, it's likely not as granular as like, okay, they can only get max 1,000 a minute. If they go over that, the world ends. So I think this would be a fine solution, but imagine your use case was you had an API for order fulfillment or shipping items, and you're rate limiting that. Like if that costs you money, tangible money in real life, you can't allow an extra 200 requests through. So the guarantees you would need depend on your business use case, right? If we need consistency across these counts, then we probably do need some data store that guarantees us consistency. And it turns out like that's what the database does for us. But we have to answer that ourselves. So I think like if you're doing rate limiting in your application today, I think a lot of people are doing it incorrectly. I actually do think an approach more robust than this, there's some timing issues here that I'm not going to talk about, but something like this is actually an ideal solution for rate limiting. But I want to say that's with the caveat that assumes the guarantees you want are inconsistencies being okay. And based on your use case, it's going to change. But these are the realities of distributed systems. And beyond that, it becomes more complicated if we handle the state problem, where we say, okay, I know the guarantees I want for the state in the cluster. There's an entire other problem of like, okay, actually, where do I spawn processes in the cluster? And this is often called process placement. And then, by the way, there's this other problem of actually, how do I find this process later after I put it somewhere? And these are really hard problems. And I think most people don't even think about this problem. So let's imagine, like, instead of a tic-tac-toe game, we have some real game that's complicated, and we're going to spawn some session for that game. And let's say that you can do that over an API request. And let's say that this game holds in like an entire game world, and it's doing a lot of potentially expensive operations. Like we probably don't want to. We can't just say whatever node that the request happens to load balance to. We can't just spawn that on the Phoenix node. We probably want to spawn that on some beefy server somewhere that holds all the game processes. And we probably want that to be load balanced. So let's say we have like 3 giant servers that can handle 4 million processes each. We want to have that load balance across each of those servers, right? So that way we don't just pick the first one and then load that up. So it's like, how do we actually do process placement? How do we load balance where we spawn this game session if it comes in from a web request? And there are ways to do this, but this remains a unsolved problem as far as like an obvious solution. And, so Paul Schoenfelder has a library called Swarm that he solved some of these issues. So there's some initiatives in some places. We have like the React core library that can handle how do we actually like find this process somewhere, but we need better tools to handle these problems. And these are things that you have to think about. It's like now that we have figured out our stateful application, we then have to think about where do we spawn the processes, how do we find them later. You can do tricks like the Phoenix long pole transport. We spawn a process on a server. We just put it on the web node that comes in, but it's the long pole web request, so it makes sense. But we spawn this process somewhere, and it waits for channel messages, and the user request ends, and then when they pull back to the server, we have to find that process to say, hey, give me your messages. So we cheat, and Jose hates this, but this is why the long pole transport's commented out in your user socket by default. He didn't want to support long polling because of the way that I did this, but the trade-off was we still support it, but it's commented out by default. And the reason why is this. So it's like, how do you find that process later when you long poll back?
and you may load balance in your next long pole to another node. How do you get back to that process we started? So we actually we take the PID that we started and we do a Erlang term to binary. So we just convert. We ultimately convert the PID to an encoded string and a token, and then we sign that and we send it back down the client. So the client actually holds the encoded PID in the browser. So when they come back up, we do a Erlang binary determ back into a PID and then just send it a message, which is pretty neat. So there are ways around this discovery problem, but ultimately, if you want to name a process somewhere, it works because that's per user, per long poll. But if you wanted to start a game server somewhere based on some game ID, we have to then be able to find that. Like if someone else joins my game, I can't just like tell them what the PID is. We have to find it by name. And that remains a hard problem to solve. There are lower level tools that exist in the Erlang community, and there are initiatives that people are starting, but this remains not an obvious solution as far as our average Elixir program is concerned. And again, like I said, we don't know where to spawn this thing. And likely, if we figure out where do we want to spawn it, like a particular 3 servers, we then want that to be load balanced for us. So, like I said, we need better tooling, and I think we're seeing initiatives happen here. Phoenix PubSub itself has always been about enabling distributed applications. Like our PubSub's distributed, and we help in certain areas, but we still don't answer all of these questions. So whether someone does a game spawn somewhere, I want it to be just this like obvious process where it's like, oh, I can just write some Elixir code, and if I know the guarantees I want, it should be an seemingly easily problem to solve as far as our users are concerned. So I think this is what really is going to allow us to eat the world. Because I think like we're already seeing, like I said, people are using Elixir and Phoenix as this stateful platform and getting incredible business value. So if we can then like solve all these hard problems where you can just come in and write a distributed program without being this distributed programming expert, I think like it's going to be, I think it's going to be so compelling that this is going to draw people into the language. So it's whether doing game server spawn or rate limit log, if you can answer the question of what guarantees do I want tooling to be there to allow you to write that program. But you still have to think about those guarantees. But having said that, like if you want to write an accounts register user function, like put that in the database. So like the solutions that we write at the end of the day, even if this distributed tooling exists, so 3 years from now we've eaten the world, we've tackled distributed programming, people are flocking to the community, like we still are likely going to have a database deployed somewhere. Like this Postgres server is going to be running on our cluster complementing the other stateful processes and all these distributed processes in our app. Like we can't, ultimately if we solve the database problem in Elixir and we're going to end up rewriting a database in Elixir, right? Like ultimately, database gives us guarantees that we need, and if we need that consistency, we need a database, and databases exist that solve all those problems today. So the database is still good for lots of problems. I think lots of boring business problems that people are solving with Phoenix are just reading and writing to the database, but people are still getting all the benefits that exist in the platform. And that's really, I guess, my goal with the initiatives in Phoenix, especially like Phoenix PubSub, Tracker, and Presence. Like Phoenix and Elixir exist to be this plumbing for you. So our goal, the initiative is still really early, but our goal is to take Phoenix PubSub, and that includes the Phoenix Presence and the Phoenix Tracker, and we want to break that down into lower level pieces and start building some solutions to some of these problems I mentioned. That way, if you can answer the guarantees you want, you can then just reach for these lower level tools. Especially like Phoenix Tracker ends up being a process group that I accidentally wrote when I was trying to write Presence. So what I'm really good at is I can solve a problem on I want to show a list of users on a web page, and that's what Phoenix Presence started as. And I solved that problem from the top down, and then Jose comes in bottom up and tells me what's wrong with everything. But no, it's he comes in and he's like, this tracker thing that ultimately Phoenix Presence is using this thing called Phoenix Tracker. And I wrote that to solve that presence issue. And then Jose is really good where he comes in and he's like, Chris, Phoenix Tracker is actually 3 separate things that you wrote and made it one thing. So the tracker is handling node discovery and detecting when nodes come and go in the cluster. It's handling replicating CRDT data. And Phoenix PubSub even, Jose was like, Phoenix PubSub is two separate things. Like there's an RPC mechanism there. So it's great. So Jose has come in and said, like, we need to break this great work that's happening in Phoenix PubSub and the tracker into smaller pieces, and then have that be a foundation for like a distributed toolkit. That way people can message another node on the cluster. It's still going to have PubSub, right? It's still going to have the process group that supports Phoenix presence, but it's going to be smaller pieces that we can then use to tackle some of these problems. And I said, just like Elixir, like it turns out the Elixir registry actually it's only a local registry only, but Elixir itself is starting to think about some of these problems as well. Like how do we discover processes? Right now it's local only, and long term I'd like to see a global registry. The Erlang OTP folks are supposed to be working on a better, like Erlang Global exists today, but it has some scalability issues depending on the scale that you're operating at. So we're kind of waiting on see if they solve all the hard problems for us. But I think whether you're using Phoenix or Elixir, like the goals are like we have like Elixir's task module. So like Jose came in and said like, wow, Erlang has these primitives which are amazing. We can spawn up little bits of concurrency, but like if you just wanted to use all your CPU cores, that was actually kind of hard to do in Erlang as far as like just being able to have cheap concurrency at your fingertips. So Jose has added tasks to the language. So like we want to, in my mind, continue to take like we have these amazing primitives and these amazing features of the language, and how can we create libraries to help you to really leverage those. If we do that, I think we really truly will eat the world. So that's all I have. Again, check out Dockyard. Give them a big thank you. There's several of us here at the conference, so if you have any questions about Dockyard, reach out to me, but that's all I got. And I don't know if we have time for questions, but where's Jim at? Jim in here? There's several of us here at the conference. If you have questions, happy to take them.
All right.
We got Dave.
Actually, no. I think what you're saying is absolutely right and really phenomenal. I just have one request, really.
Sure.
And that is all of these new things that you're thinking of doing, and some of the things you've already done, like PubSub, can we keep them separate rather than bundling them all into one big thing? And the same goes on the Elixir side as well.
Yep.
Because I think one of the mistakes that I'm seeing now is that we're getting these coupling happening between all of the different libraries, which means you can't pick and choose, and you can't use them in contexts that they weren't designed for.
Gotcha. Yeah, so I would say yes. So like it's too early to talk about, but we've started work on breaking down the Phoenix PubSub into a new library. And it exists under the Phoenix Framework GitHub organization, only because we were going to make it separate, but like PubSub is my baby, so like I'm not ready to let it go yet. But it will be, the namespace of the library won't have Phoenix in it, so it will be totally outside that idea. But you're right. So I have. Like the longer story is like I have thought about this where if we make this distributed tooling library that does PubSub and RPC, and then however we end up rewriting presence on top of it, like I do see it start getting pretty large. Like if we're starting to have its own CRDT implementations, like it would be nice to like at some point we can't just throw everything in this library, right? Because it will eventually become a database. Like it will accidentally like you'll use this new library and it turns out to be. So, but yeah, you're right. So I think I will definitely keep that in mind. It's a good point. I do see it start getting pretty large. Like if we're starting to have its own CRDT implementations, like it would be nice to like at some point where we can't just throw everything in this library.
Well, I agree with Dave. What you guys are doing is great because you're bringing this knowledge that we have about stateless, and now we are going into state. But let's not forget that the Erlang people have developed some great tools. You were talking about ETS. We also have, Erlang also has amnesia. They have solved a lot of the problems that you have talked, and you can have amnesia, RAM copies, and fragmentation, and a lot of the problems that at the beginning we try to use ets or dets, or then we go to Postgres. There's amnesia in the middle that can solve some of the problems too.
Yeah, absolutely. Yeah. So amnesia for me is there's definitely some I feel like people using Amnesia really well, like, don't get me wrong, I think there's some amazing engineering there, but the people that use it well, I feel like you have to be like an Amnesia expert. Because for me, especially, like if I deploy a system for a client and they end up with a fragmented or corrupt Amnesia table, like your database is ultimately like sacred, right? So like if your data is sacred and you end up with a net split, and you have diverging tables, it's like I'm personally not comfortable coming in and trying to solve that. So I wouldn't say never use Amnesia, but I've never been comfortable enough to not use a traditional data store if I need that kind of consistency. But I have heard people using it, to massive success. So your mileage may vary. I'm personally not comfortable coming in and trying to solve that. So I wouldn't say. All right. Yeah, just find me. I'll be around all day. So thanks a lot. But I have heard people using it, to massive success. So your mileage may vary. All right. Yeah, just find me. I'll be around all day. So thanks a lot.